Hey everyone, today we're going to be looking at atomic physics, and this is the first lesson in this particular topic. It's going to focus a little bit on the history of the atomic structure, as well as the behavior of some of the parts of the atom, or more generally the atom itself. So when we talk about atomic structure and the history, we want to first begin with the discovery of the electron. This is generally credited to being discovered by one J.J. Thomson in the late 1800s, early 1900s. And in fact, he actually didn't call it an electron. He had a much different name for it. He actually called it a corpuscle. But nevertheless, he kind of knew its importance in the structure of matter. He knew that it was negatively charged. But what was really difficult at the time, and the scientists are building towards trying to figure out what's the charge and what's the mass of this electron. How can we know? And what they can't quite figure out at their very beginning in the 1900s is either one of those, but they're thinking maybe they can figure out a charge to mass ratio, so one divided by the other, without actually knowing either of them. And so this is the kind of elaborate setup that they put an electron through to figure out this particular ratio. It's actually quite clever. It uses electric fields and magnetic fields in the following way. So the first is, let's say you have an electric field maintained by two parallel plates, perhaps. So you have an electric field that points downwards. And so remember, an electric field, if we think way back when we first described electric fields point in the direction that a positive charge would flow in. So when we send our negative electron through, it's going to actually bend upwards. So we're going to have an electric force on the electron. And so here's kind of like a force diagram. We're going to have an electric force that points upwards. And then if we also combine that with a magnetic field where it points, the electron is moving this way, the magnetic field points into the page, and so the deflection is the middle finger pointing downwards in a sense. So the magnetic field is going to cause a force, so the magnetic deflecting force will be downwards if we point the magnetic field to be into the page. So that's kind of this particular diagram. You can do that for yourself, and you'll find that when you try to stick out the rest of your fingers, the middle finger is kind of pointing downwards in the same direction that the electric field points. So that'll set up a way for you to kind of be able to tune both the strength of the magnetic and electric field so that the forces are equal. So that as this electron passes through both of these fields, it's bent downwards by the magnetic field and it's bent upwards by the electric field, and so it just kind of like stays relatively straight. So that means the electric force is equal to the magnetic force. Well, electric force is Q multiplied by the strength of the electric field, which is equal to QV strength of the magnetic field. And so when we try to solve for things here, it'd be great if we could solve for the charge, but we don't know how fast the electrons are going. So what we can actually do is we can cancel out the charge, because it should be the equal charge for the electron on both influences. And so what we can actually solve for is the thing we kind of don't know. The speed of the electrons through these fields should be the ratio of the electric field strength divided by the magnetic field strength, so long as the electron doesn't, I guess, get influenced more by one than the other. So it has to be that the forces are equal, which means there's no field that kind of beats out the other. So we can figure out the speed. So let's actually try this with a few numbers. Let's try an electric field with 50 kilonewtons per coulomb and a magnetic field with 0.5 Tesla. So 50 kilonewtons, so 50,000 newtons, divide by 0.5, and you get a speed of 1 times 10 to the 5 meters per second. So that's 1 times 10 to the 5. Okay, so now that we have our speed, like I said, this setup was kind of elaborate. Remember, we're trying to get the ratio, and so far all we figured out is how fast the thing is going. Seems not great. But what then is going to happen is that this electron moving this way, actually, I want to draw this a little differently, should make sense soon enough. The electron that's moving this way, and now that we know its speed, is now what we're going to do is we're going to shut the electric field off. So the magnetic field is still operating this way. And the electron is moving to the right. So what's our deflecting force here? So here we have a deflecting force downwards. So once I guess the idea is once you turn off the electric field, the magnetic field is now the only thing at play. And so the electron that is moving to the right, and now that we know its speed from this particular clever setup, we can understand the magnetic force is still acting on the particular electron, and a force means acceleration. So if something moving kind of this way, we have an acceleration that's directly perpendicular. So what this can somewhat remind us of is, like, after a little bit of time, this particular electron is going to have deflected down this way. But our force is going to point inwards. And so eventually this is going to mimic circular motion. And so this is kind of the idea. Goes in a circle now, or spirals in a sense. So now we have that the net force is equal, the only thing acting on this is the magnetic force, but it's circular motion. So we can say mv squared over r is equal to qvb. And now what we want to do, we can cancel out the velocity here, divide by m, divide by b. So that leaves us with q over m. That's when we divide by m, divide by b. We have v over r multiplied by b. So a speed that we just measured, a radius that we can most likely calculate, and a strength of the magnetic field that we know will give us what the ratio between the charge and the mass is. And so if we actually use our B value start with our V velocity value of 1 times 10 to the 5 meters per second, and a B value of 1.42 times 10 to the negative 5 Tesla, and a radius of 4 centimeters. We actually plug this in, the charge to mass ratio turns out to be roughly 1.76 times 10 to the 11 coulombs per kilogram. And well, this is now kind of useful. This provided pretty big insight to its comparison with the nucleus of an atom. But what's more important is what's going to then be done with that particular charge to mass ratio. And so this is all being done in the early 1900s. So now enters a new scientist. His name is Millikan. And again, these are just kind of like clever setups to try and exploit the forces at play here. But he's kind of looking at the Millikan oil drop. You'll also notice that for this, well, shouldn't gravity act on this particular particle? And the answer is yes, but it's assumed that it's so small that these two things are going to be so big compared to the gravitational force that we don't actually have to include the gravitational force. Millikan's oil drop is now starting to get in the range of things that do have to incorporate the gravitational force. So it's just drops of oil, but they're affected by gravity. So it's kind of like taking drops of oil with a mass 8.2 times 10 to the negative 15 kilograms. And everywhere that we kind of pull numbers, we also like to say where those come from. So in Millikan's experiment, he was able to measure just with like a microscope, I would imagine a microscope, the diameter of the oil drops. And so if you know the density of the oil and you know the diameter, diameter is going to lead you to the volume of a spherical oil drop, and then the density, combine volume density, and you're going to be able to figure out the mass of the oil drop. So if you have that, this is kind of set. Here's your oil drop, and you know there's some amount of charge on it. The reason that you know that is because you put it in an electric field and it actually behaves as if there's charge on it. So normally it just falls like so. Gravitational force is going to pull it down. We're at the kind of range of mass, I suppose, that is influential when you have a sufficient electric field. The two balance out. Now, we can throw some numbers in here, and we're going to get to that. However, before we kind of do, well, let's throw at least the 9.81 in, and the electric field strength being maybe 10 to the 5. What we're going to be able to calculate is the actual charge. And before we get into the results of this, our gravitational force balancing with our electric force, mg is equal to q times E. The results of this are a little bit strange, a little bit different, because Millikan doesn't really know how much charge is on the oil drop. He's got a thing that sprays it with charge, but he doesn't know how much. And so he kind of compiles all of this data, and he says, he makes the following observations. He observes that there seems to be a minimum charge. it seems that the minimum charge that he gets is a particular quantity. If we actually just kind of plug in all these numbers, the Q is mg over E. It is 8.2 times 10 to the negative 15. We plug in all these and calculate, we're going to get a number of 8.04 times 10 to the negative 19 coulombs. So calculating, we get something along these lines. Sorry, I digress a little bit, but Millikan finds that there's a minimum charge. There seems that the lowest it can be is this particular number, roughly 1.6 times 10 to the negative 19 coulombs. And not only does he take a look at this and say that seems to be about the minimum charge, he notices that anytime he calculates for a charge, like in this particular case, we take this number and divide it by the 1.6, it's fairly close to 5. And so Millikan makes the observation that the charge is always equal to n multiplied by this 1.6 times 10 to the negative 19. It's always some type of multiple of this charge. So n can equal 1, n can equal 2, n can equal 3, dot, 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 n could equal 5, kind of like it does here. You may say, well, it doesn't equal exactly 5, and you're kind of right, but as experiments go, we're trying to minimize the error in this. So we're trying to use the best values that we have, and how certain are you that this is the exact mass and that this is the exact strength of the magnetic field? So within error, you're getting a quantity of 5. And so every time he does this, he gets kind of a within error integer multiple of this minimum charge here. He says, okay, the smallest thing we know that has a charge is an electron. So he says the charge of the electron is 1.6 times 10 to the negative 19 coulombs. He says it's roughly that, and we have a much more accurate number today, but this is pretty good for just kind of this oil drop experiment, which I hate to say it, that I hate an aspect of physics, but this particular experiment, as cool as it is, as clever, I remember doing it in college, and this sucked to do. This was I have memories of how much I did not like doing this particular experiment. However, that being said, a quantity of the charge is found. Okay, well, perhaps we can use that with the charge to mass ratio and get a understanding of the mass of the electron. So the charge to mass ratio is this 1.76 times 10 to the 11 coulombs per kilogram. And we now kind of have an idea, after Millikan's experiment, that the charge is roughly 1.6 times 10 to the negative 19 coulombs. And now we can maybe solve for mass. It turns out that the mass of the electron, when you solve for this, we can do it ourselves, 1.76 E11 divided by, 1.6 E negative 19 divided by that. You get roughly the quantity that we actually use today. We get 9.09 times 10 to the negative 31 kilograms, and that's very close to the mass of the electron that has been calculated with some sharper tools, we'll say. All of this being said, it's the early 1900s, and set out discovering the electron and kind of knowing that it has an electric charge. Well, what is that electric charge? We figured it out with some very clever setup, and through that we can also figure out the mass. So that's quite useful to know, and led us to even more discoveries. That should be a good place to end for our first lesson on atomic physics.